MSCI 445 presentation on cloud computing networking concepts. At a high level, what is cloud computing? Cloud computing is essentially virtual on-demand availability of compute resources. This is usually done through virtualization of compute resources. The three most important protocols on cloud networks are TCP, UDP, and SNMP. TCP guarantees the integrity of the data being communicated over a network. An integral part of this is TCP optimization, which avoids TCP slow start and checks the bandwidth between edge servers to create a persistent web connection between on-premises networks and edge devices. Another important protocol is UDP, which is an alternative to TCP. It establishes low latency connections, which reduces transmission time, but comes at the cost of not guaranteeing consistent data transmission. And SNMP is a way of different devices on a network to share information with one another. It allows devices to communicate even if the devices are in different hardware and run on different software. At this point, you may be wondering, how do public cloud networks maintain security? Some key questions to ask when it comes to cloud computing security is, how is data shared securely across the cloud network? What if a cloud server and an end device, such as the user's laptop, want to share private data? Without secure connections between two parties on the network, a malicious attacker can view and edit data. What's the solution? The solution is HTTPS, and this is done through TLS. HTTPS is initialized through Transport Layer Security Protocol, which essentially offers a secure and reliable method to establish connections between server and devices through encryption. TLS is how HTTP transforms to HTTPS, essentially creating an encrypted secure network between the server and the client. There are two main concepts of TLS, the TLS handshake and the TLS cipher suite. The TLS handshake is how the secure connection is made, while the TLS cipher suite is how the encryption process is selected by the server and the client. TLS handshakes are a series of datagrams and messages exchanged by a client and a server. What's the purpose? The purpose is to validate the identity of both the client and server. In addition, it's to establish encrypted communication channel between the client and server, and to establish a reliable network industry standard for HTTPS that can be used by all browsers and all devices. There are two main key aspects to TLS. The key exchange will be done using asymmetric key encryption, and the subsequent communication will be done through symmetric key encryption. The first step of the TLS handshake is to establish the TCP connection. This is done by the client sending a synchronized datagram to the server. The server responds with a synchronized acknowledged datagram, and the client responds with an acknowledgement datagram. At this point, TCP connection has been established, and we can initiate the TLS handshake. The second step of the TLS handshake is the client hello and the server hello. The client hello is when the client initiates the handshake by sending a message to the server. The message will include which TLS version the client supports, the TLS cipher suite supported by the client, and a string of random bytes known as the client random. Then the server will respond with a server hello message. In the reply to the client hello message, the server sends a message containing the server's SSL certificate, the server's chosen cipher suite, which has been selected from the client's supported TLS cipher suite, and another random string of bytes that's generated by the server. These random strings of bytes will be important down the line in the TLS handshake. The third step of the TLS handshake is for the client to authenticate the server certificate that was issued in step number 2. The client verifies the server's certificate with the certificate authority that issued it. A common certificate authority is Google's certificate authority. This confirms that the server is the authorized owner of the domain and that the client is interacting with the actual owner of the domain. The certificate authority is a key component of the TLS handshake, and therefore the World Wide Web depends on certificate authorities. Step number 4 of the TLS handshake is the key generation and key exchange. Essentially, the client will create the pre-master secret number, which is a random number that will be encrypted using the server's public key. The server's public key is also known as the server's certificate. Then, the server will use its own private key to decrypt the public master secret number that was transmitted by the client. At this point, both parties have the same set of tools to generate their master secret. The tools that they have is the random number generated by the server, the random number generated by the client, and the pre-master secret number. At this point, the master secret is generated at both ends. Previously, we mentioned that asymmetric key encryption and symmetric key encryption are used in TLS. Essentially, asymmetric key encryption is used to transmit the data that will then subsequently be used to generate the master secret. That way, both parties have public and private key pairs that can be used to encrypt and decrypt data securely. But at this point, because both parties have the same master secret, they can now subsequently use symmetric key encryption to have low latency and quick transmission. The final step of the TLS handshake is for both parties to confirm that they have the same symmetric key. Essentially, the client will send data encrypted with the master secret and the NSSL handshake data segment to the server. The server will subsequently send data encrypted with the same master secret and SSL handshake to the client. At this point, TLS has been established. The second important part of TLS is the TLS cipher suite. The purpose of this is for the server and the client to decide on a compatible TLS connection type. Due to different versions of TLS on end devices, TLS connections must ensure that there's a compatible version selected both by the client and the server. The server will receive a list of TLS cipher suites from the client that the client supports. The server will then select the most secure TLS cipher suite common between both participants. This was seen in one of the steps in the TLS handshake. The main aspects of the TLS cipher suite that must be decided are the protocol version, the key exchange method, the authentication method, the cipher encryption, and the MAC hashing algorithm. The first component of the TLS cipher suite is the protocol version. The server must establish which version the client device is compatible with. The server will select the most up-to-date TLS version that the client has. For example, currently TLS 1.2 and TLS 1.3 are the most secure and the newest options. The most outdated and subsequently not as secure option is SSL version 3. Another important part of the TLS cipher suite is the key exchange method, which establishes how the TLS handshake symmetric key exchange will occur. Some options are the Diffie-Hellman, which is a forward secret cipher, RSA, and elliptic curve Diffie-Hellman, which is perfect forward secret cipher. This results in smaller key sizes and increases the key transmission speed. An important component to remember about TLS is it is very CPU intensive to result the encryptions. Therefore, smaller keys results in faster transmission speeds, which is key. The third component of the TLS cipher suite is the bulk encryption algorithm. Essentially, this algorithm is used in the symmetric key encryption process. It establishes the algorithm that the symmetric key will use when encrypting the data. And an example of this is Advanced Encryption Standard. Essentially, this is integral for the symmetric key encryption. The fourth component of the TLS cipher suite is the authentication method. This establishes how the client will authenticate the server's certificate, also known as its public key. Essentially, the server will send the client device its certificate. The client can then check the certificate to ensure that the server is authentic. To check the certificate, clients must send the certificate to a certified certificate authority. Types of authentication methods are RSA and elliptic curve digital signature algorithm. The final component of the TLS cipher suite is the message authentication code, which is also known as the MAC. This is the hashing algorithm that both authenticates messages and ensures data integrity. This is an example of the TLS cipher suite. It essentially contains the 5 components that we spoke about, which has to be determined between the client and the server. Essentially, the client will send a list of these values to the server, and the server will select the most secure combination of these values. This is another example of a TLS cipher suite that has been sent by the LinkedIn server on my local machine. Essentially, you can see in the cipher, the LinkedIn server is dictating the optimal decision for the TLS cipher suite. This is another example of a TLS cipher suite, but here we're focusing in on the hashed server certificate. As you can see in my terminal, I'm able to view the hashed value for the server certificate that has been sent by the linkedin.com server. An important cloud networks communicate with external clients and servers. How does a DNS server know which IP address to route client requests to? How do DNS servers keep track of every changing and dynamic IP address due to rapid deployment of virtual machines? How do multiple servers share the same valid server certificate for TLS? These are all important questions to ask, especially with the given virtualization of computing resources on cloud networks. The answer to our question is reverse proxies. Essentially what a reverse proxy is, it is a dedicated server on our network that accepts all requests from servers and devices from outside of our network. It is essentially the gatekeeper between our internal network and all external devices and servers. Essentially how this is done is that administrator will add the new server into our network. This will be a reverse proxy. This server will have administrator rules that dictate that it can accept IP addresses from outside of our network, while all other servers in our network will only accept IP addresses from internal devices. Essentially, this is whitelisting and blacklisting IP addresses. Another critical rule is the administrator will create rules for how the reverse proxy will parse HTTP requests. Essentially, this is how the filtering is done. The reverse proxy will parse the HTTP header from incoming client request. Then it will maintain route mapping rules that help the reverse proxy to identify which internal server to route the request to and which request to block. There are two main use cases for reverse proxies. One is security and the other is scalability. And this all stems from the fact that the reverse proxy is the gatekeeper of all external requests. How reverse proxies establish security on our network is they are the single IP address that all external clients can access. This essentially prevents attackers from identifying the direct IP address of our internal backend servers. This also allows for an abstraction layer between the client and our backend server infrastructure, which makes attacks harder as the server infrastructure is hidden. Furthermore, TLS termination allows for reverse proxies to deal with TLS ciphers a lot quicker and reduces the workload. Furthermore, the reverse proxy can act as a firewall, which prevents distributed denial of service attacks by throttling and limiting requests coming from the same client IP addresses. Furthermore, it can blacklist certain IP addresses from specific regions. It can prevent attacks from content and web scraper bots, and it can also prevent cross-site scripting attacks. Now we will discuss how reverse proxies introduce scalability into our network. One method of this is through server load balancing. This is where reverse proxies retain the status of all internal servers and the number of possible requests that they're dealing with currently. This allows the reverse proxy to route new requests to a server that has the CPU capacity to deal with that new request. This routing can be done through multiple methods such as round robin, least connection, agent-based adaptive balancing. Furthermore, reverse proxies can introduce static data caching, which allows for the reverse proxy server to retain data that is used frequently, specifically static data, to reduce the amount of calls needed to backend servers. Therefore, the reverse proxy itself can sometimes respond to certain requests and also reduces the amount of data transmission within our network as data is stored locally on the edge network through the reverse proxy. Here is an example of how reverse proxies in this use case are used as API gateways and deal with routing particular calls to a specific server that can deal with that request. Here, as you can see, it parses the URL path and looks for the corresponding server that matches that path. These paths have been dictated by the administrator when the reverse proxy was created.